Before a massive shunt reactor is safely synchronized to the high-voltage grid, it must pass a rigorous, multi-domain validation. This protocol verifies three specific operational layers: dielectric integrity, electromagnetic properties, and the protection and supervision systems. When project specifications, manufacturer instructions, and international standards like IEEE or IEC conflict, field engineers operate under a strict governance rule: apply the most stringent approved requirement. Before initiating any test, the reactor requires complete isolation. This means confirming lockout-tagout procedures, verifying a safe discharge status, and implementing a confirmed grounding plan. The very first physical action on the asset is removing dust, moisture, and conductive contamination from all bushings and terminal surfaces. If surface contamination remains, or if safety boundaries are loose, the resulting microampere leakage data will be invalid. A failure to clean the asset renders the entire commissioning protocol useless. Test 1 validates winding insulation resistance using a 5 kV DC tester. This schematic details the required test connections. The megger is wired directly to the R, Y, B, and neutral bushings. Technicians record stable readings for 10 minutes, calculating the polarization index by dividing the 10-minute reading by the 1-minute reading. The absolute insulation resistance must exceed 10 megaohms, and the resulting polarization index must be at least 1.25. For test 2, we measure core and frame insulation. This diagram emphasizes a critical step. Earth and core-to-frame links must be physically removed before testing. We apply 1 kV DC for 1 minute across 3 paths: core to earth, frame to earth, and core to frame. Failure to remove those physical earth and core links creates parallel electrical paths. This masks actual insulation decay and yields false positive test results. Test 3 verifies winding resistance. This schematic illustrates the requirement to use a calibrated milliohm meter with Kelvin leads, connected securely across the R to neutral, Y to neutral, and B to neutral phases. Engineers record the ambient temperature alongside every raw resistance reading. These values are then corrected to a 75 degrees Celsius baseline using the approved copper temperature correction formula. Test 7 measures phase impedance. This upper schematic shows the setup for a protected 380-volt three-phase injection supply routed directly into the winding terminals. Once energized, technicians measure the phase voltages and currents for each winding path. Using those values, we calculate the impedance per phase with this formula. The results are directly compared against the factory baseline data and approved project tolerances. Gathering phase-balanced, temperature-corrected data is the only reliable method to confirm structural winding continuity and prevent destructive magnetic imbalances during live operation. Test 5 evaluates the dielectric condition using tan delta, or power factor testing. This diagram illustrates the Doble test set applying a 10 kV AC test voltage across the required insulation paths. During the test, the instrument captures 4 specific metrics: charging current, watts loss, capacitance, and AC resistance. The strict acceptance limit requires the power factor to remain below 0.5%. There is zero tolerance for abnormal current, flashover, or unexplained phase deviations. Test 6 measures the oil dielectric breakdown voltage. The process starts by cleaning a test cup with dry hydrocarbon solvent, filling it with the oil sample, and allowing it to rest for 3 to 5 minutes so all internal bubbles clear. Voltage is then applied at a specified ramp rate until complete dielectric breakdown occurs across the sample gap. New insulating oil must withstand at least 30 kilovolts. For oil already in service, the threshold is strictly above 26 kilovolts. AC tan delta and oil breakdown tests are mandatory because they expose microscopic moisture and conductive flaws that standard DC maker tests simply cannot detect. Test 4 calibrates temperature sensors by immersing the oil temperature indicator bulb into a heated oil bath at defined reference temperatures. Next, we inject a secondary current to mimic winding thermal load, recording the temperature rise over 45 minutes. Test 8 is the supervision functional check. This table lists protective devices like the Buchholz relay, pressure relief devices, and gas detectors. Each device must be forced physically to verify the signal reaches the marshalling kiosk. The validation chain must be absolute. An alarm triggers locally, enunciates on the HMI workstation, and successfully transmits via the network gateway. For Test 9, technicians perform insulation checks on cooling fan motors through the terminal block, measuring starting and running currents across all 3 phases. Finally, they execute a phase loss test by dropping one phase, verifying the protection logic correctly trips. The internal health of the asset is meaningless if the external supervision and cooling logic fails to protect it during a live fault condition. When test results deviate, protocol dictates strict troubleshooting paths. If the winding polarization index falls below 1.25, engineers must immediately investigate bushing cleanliness and ambient humidity before diagnosing an internal winding failure. A near-zero reading on core-to-earth insulation almost universally indicates an administrative failure to physically remove the grounding test links. If impedance values show unexplained deviations, crews must perform an immediate physical inspection of termination tightness and re-verify the ambient temperature calculations. Before handover, the process reaches an absolute administrative hold point. All temporary forcings, bypassed trip contacts, and test alarms must be formally cleared and documented. The final witness signs off on the procedure only after full physical confirmation that normal automatic operation is completely restored. A shunt reactor is ready for grid synchronization only when all 9 validation layers align exactly, without a single bypass, compromise, or uncorrected variable.